doing like a big hypothesis test. And if you read through the instructions, the hypothesis is that this person's sales of $275 are greater than the average sales in the Pacific region. Okay, so I don't want to give away too many answers. So make sure you use the Pacific region when you do your tabs. But just so I don't give away the exact numbers, I'm going to use the data set for the West, North, Central region. Okay, but again, you want to use the Pacific region because that's where this person's from. You wouldn't want to obviously compare his sales to a different region because they have different characteristics. So if I'm doing a hypothesis test and if my goal is to test the claim that I have better than $275 in sales, like if I think I'm doing, or if my, sorry, let me rephrase. If my goal is to test a claim and say that my sales are above average, then my alternative hypothesis is that my mean, which represents my average, is greater than the, well, it depends on what the actual population mean is. Let's say it's like 199. Okay, so in order to formally state that hypothesis, okay, this is my H1, my H sub 0, that's your null hypothesis. I just made up the number 199. Here, let's go figure out what that number is supposed to be. I'll show you the steps you need to do. It's real quick. You just need to find, like we've done before, find the mean of the right column, the correct column here. We're talking about the cost per square foot. He's saying his cost per square foot is $275, and he thinks that's better than the typical cost per square foot. And so, does the numbers support his claim? Well, what we do is we need to first calculate the mean for this column. So type equals average, open a parentheses, and then I'm going to type E6, and then I'm going to use shift to get to the colon key. And then I'm going to scroll all the way down to figure out what the last cell is. So E1, 1006 is the last part. And then hit enter. That's an easier way of doing it rather than clicking and dragging. So the mean for this region, for the West, North, Central region, is $117 per square foot for the home. So back to that hypothesis that we're supposed to state. For this person, if they think they've done better than average, then the null hypothesis would be that the mean is $117. That there's really no effect, because the null effect model, the null hypothesis is like the no effect model. It means nothing's really happening. It's the alternative hypothesis that our p-value is supposed to tell us whether we can support that conclusion or not. Our alternative hypothesis is the one that we're trying to test. We're trying to test to see if their mean is greater than the typical mean. Okay. I'm just thinking for a second. There's the null and the alternative hypothesis that this person's mean is greater than 117 for my data set. Like I said, you want to use the Pacific data set though. Okay, we defined our population parameter. Actually, to be more explicit there, the population parameter would be the population mean for the region, which is actually something we don't know. Okay, it's just something we have to estimate with our sample. So our population parameter, we're estimating it with our 1001 samples. I just estimated my population parameter to be 117. Write a null and alternative hypothesis, which is what I have over here, the null and the alternative. Specify the name of the test that you use, whether it's a left-tailed, right-tailed, two-tailed. So you can determine whether it's left-tailed, right-tailed, or two-tailed by looking at your alternative. The alternative for my hypothesis test is that I'm testing to see whether my mean is bigger than some value, right? So that is, in math, if we get bigger, we go to the right. On our number lines, the lowest numbers are always on the left, the highest numbers on the right. So this is a right-tailed test. If you were to draw that normal distribution, you're trying to see if your test statistic lands off into the right tail. So this is a right-tailed test because it's greater than. If we were testing that the mean is less than 117, that'd be a left-tailed test. Identify your significance level. They say it right up here. Your alpha is 0.05, so that's the significance level you're going to use. Data analysis preparation. Describe this sample summary statistics. Okay, so it sounds like they're looking for us to just do what we did in the other assignments: calculate a mean, a standard deviation, and a histogram. Make sure to check back on the previous video I made last week to see how to do that on a histogram in Excel. You could use just an online software too. You could just Google search histogram generator too. We're not being picky about where you get your histogram from. Check assumptions. Find the test statistic and significance level. So when they mean check assumptions, before you conduct a hypothesis test, there's often choices. I mean, in this class we don't have a range of options, but there's something called non-parametric statistics that you could use if you are worried about, if you need something that's a little bit more flexible. But in general, the assumption that you want to test is you want your data set to be approximately normally distributed. Okay, that's less of a concern if you have a large sample size, like we do. We got over 1,000. It's 1,001, so that's a pretty big sample size. We're probably okay. The central limit theorem most likely kicks in, and the mean is most likely approximately normally distributed. Because the central limit theorem says if you have enough data points, then you can be reassured that maybe your data set doesn't have a normal distribution, but the mean is going to be approximately normal. Okay, so when you talk about your assumptions, you should probably reference the central limit theorem there. The central limit theorem tells us that our mean is approximately normally distributed because we have a really large sample size. So we've talked about all these things before: shape, center, and spread. What does that histogram look like? Does it have some gaps? Does it look normally distributed? Does it have a lot of spread or a little spread? Is it centered in near one value? Okay, and then we just talked about the conditions. Okay, because of the central limit theorem, when you have a large data set, then we can be relatively reassured that that primary assumption's validated. Another assumption is that your data set is independent and identically distributed, which means that picking one house doesn't impact your chances of picking a different house, right? The crazy example I always used when I taught in the physical classroom was, if you were to line up a bunch of students and ask them, what did you think of lunch today? You talk to the first student, you say, what did you like lunch today? And they say no, and then you punch them in the stomach, and then ask the next student, did you like lunch today? His response is dependent on what you've done, right? It's dependent on your sample because you punched him right after. It's affecting all the other data points. It's unlikely that picking this house that was $109 per square foot changed what type of house we picked next. We weren't like, this is 109. We need to go find a house that's cheaper. We can be relatively assured that whoever did this data collection knew what they were doing with statistics and knew to take a random sample. But that's one thing you could comment on. Assuming that we've got a truly random sample of houses, then that criteria has been met. Okay, so the calculations. This is probably what people are usually watching the videos for. Determine the appropriate test statistic. So this is a mean, right? We calculated a mean, and we're comparing it to another mean. Where is it? Up here, they say he has an average cost per square foot. This person has an average cost of $275. So this is a hypothesis test of means, and we have two main tools for that. We can do a z-test or a t-test, and the formulas are almost the same, but the difference is which table you use. Okay, a z-test can be used if you know the population standard deviation, or sometimes it's just fine to use it if you have a huge sample size, like in this case. But in general, you want to use a t-test when you have a sample because you don't know the population standard deviation. And then, I mean, the instructions they give you is a t-test anyway down here. So calculate the p-value. So that's where we're going to want to use one of these functions. So they give you all three. This is for a two-tailed test. Look, this is a one-tailed hypothesis test because it's only one direction. It's the right side. So we want to use this one. So I'm going to type equals t.dis.rt. The RT means right-tailed. The test statistic, I actually don't have that, so hold on. before we do that. The test statistic is found using the t means formula for hypothesis testing, and they say it's right here. You take the mean subtracted by the target divided by the standard error. And it depends. I guess this is not traditional language. It depends on what they mean by target. You could switch these up, and depending on how you set up your hypothesis test, you're going to be fine. But the way we've set up our hypothesis test is that the mean we're testing is 275 for this person's house, subtracted by the population mean, which we approximated with our large sample size, approximated 117, and then we need to divide it by the standard error, it should say. Good, it does, yep. Remember, the standard error from what we've done in zyBooks is not the standard deviation. Like, this is the mean. We need the standard deviation, and we want stdv.s. You would use stdv.p if it was population, but start on E6, and I forgot what the last number was. E1006. So there, we got the standard deviation. But remember, the standard error of the mean, here, this is all to calculate our t-value. The standard error is found by taking the standard deviation and dividing it by a square root of the sample size. Okay, square root of n. So our sample size, they say, for all these regions is 1001, right? So if we need to know what the square root of n is, I'm going to type equals sqrt, open the parentheses, 1001, close the parentheses, and then Excel can calculate the square root for us. And now we're finally ready to calculate the standard error. The standard error is found by taking the standard deviation and dividing it by the square root of n. So 0.979, I'm going to say 0.98, just to approximate. So just watch out for that. That's one thing I have to look for, is that students know that when you're doing a t-test, it's the standard error, not the standard deviation that we divide by. So I shouldn't be seeing 31 down here. Okay, it's 31 divided by the square root of n, like we saw in zyBooks. Okay, so that's what we need to calculate. We need to take 275, subtracted by 117, divided by 0.98. Mine is huge. That is a huge t-value, okay? You won't get a t-value that big because you're doing the Pacific region. The mean will be closer. So that you need the t-value because now you can calculate the p-value, and that's using the formulas that they give us down here. So I'm just making a note for myself. This is the p-value. Type equals t.dist.rt because I'm a right-tailed test. And my test statistic I just got up here is 161.22. And now the degrees of freedom, when it's a one sample test like this, when we're calculating test statistic for one mean, it's just n subtracted by 1. So 1001 subtracted by 1 gives us 1000 for our degrees of freedom. And there's my p-value. It's so close to 0. It's not exactly 0, but it's so close to 0 that the computer just gave me out 0. But that's because I'm using the wrong data set, right? I didn't want to give away the answer. Let's say we had a t-value of 3. That's too high. Let's do 2.4. Okay, let's say that's what you get, just to show you what a realistic one might look like. The test statistics is 2.4. Let's say that's what you get. Same degrees of freedom. So if you got that for a p-value, 0.008288. Remember what a p-value tells you. The p-value tells you the probability that you get this t equals 2.4 or bigger, given that the null hypothesis is true, that the mean really is what we say it to be. Okay? So it's kind of like a backwards way, but it's unfortunately the way we have to do it in order to make the math work out. It's a backwards way of testing this alternative. This is a really low p-value. It's a really low chance that the null hypothesis is true. So that means we reject the null in favor of the alternative. Okay? If your p-value is less than alpha, you get to reject the null hypothesis and claim there's evidence for your alternative. There is evidence that this guy's sales are bigger, according to like the data just grabbed. Okay? But again, those are hypothetical values. You got to do the calculations with the actual data set so I don't give away the answer. Using the normal curve graph as a reference, describe where the p-value and test statistic will be placed. So maybe I can draw a quick picture. That's for something else. You don't have to worry about that crazy stuff. So this is the normal distribution. I don't think you have to draw a picture. I think you just have to describe. I'm just drawing a picture for you. If you got a t-value of like 2.4, like I just made up over there, that would be off to the right because t equals 0 is at the center. Okay. T equals 0 means it's perfectly split, a 50-50 chance either way. So t equals 2.4. That's to the right because it's bigger than 0, and that would be pretty far right into the tail. And so the p-value is this area. It's the area that corresponds to your alternative hypothesis direction. So since we have a right-tailed test, the p-value is this area over here. There's 0, what was our p-value? 0.008 something? That's the area. I mean, the whole thing, this whole area adds up to 1. So 0.008 or 0.8% of it is this tail over here. So I think that's what they're looking for in that part. Discuss how the p-value relates to the significance level. That's what we just talked about. You compare your p-value to your alpha to 0.05. And then if it's below alpha, you reject the null in favor of the hypothesis. And if the p-value is above your alternative, if your p-value is above your significance level, then you fail to reject the null hypothesis. And then you can talk about your conclusion based on what that p-value is. I think that's everything. I think that's all the nitty-gritty stuff. Just make sure to use that document that's linked in the rubric. Yeah, right here. Just fill in those places as you work on it.